So, welcome to this lecture. So, now I'm going to start a new series of undergraduate physics. I'm talking about rotational motion. So, here I started with the basics of rotational motion. So, let us classify motion, right? First of all, classification of motion. In general, we will classify motion into two types. One is the translational motion, and another is rotational motion. There are two types of motion, right? So that means when we apply certain force on some particle, say some particle will be here or some object is here, and if I apply force in along this direction, then it starts moving along this direction. But when some object is tied with something, say it is tied somewhere here, and if I apply force in this direction, then it starts rotating this direction. Then such type of motion is known as rotational motion. So both type of motions are very important in physics. So, but in this chapter, I will mainly talk about rotational motion. So rotational motion is very important. And it helps to understand various concepts. So, for example, first example is motion of electron. Under the rotational motion, I will talk about motion of electron around the nucleus. It's example from the nuclear physics, quantum physics or the quantum mechanics. And another example is from the classical world. It is the motion of planet. Then another example is motion of wheels of a car. And then another example is the motion of flywheel. So these various examples of rotational motion, and similarly we can talk about so many other examples, right? So I will start with certain basic things here. Some basic things. So let us consider the motion of a particle along the circumference of a circle. Let me do one thing. Okay, so let me just a minute. Let me draw a circle. Say an object is supposed to move the particle is supposed to move over the circumference of a circle, and say it is at any time it is making an angle theta with the x-axis, say it is x-axis and say it is y-axis. So, but after some time, this particle will reaches at another point. Let me call this as point Q, and let me call this angle as theta prime. So that means I am considering the motion of a particle on the circumference of a circle. Motion of particle on the circumference of a circle, and say at any time t, and after time t plus delta t, particle will be at point Q. So that means at point P, particle is making an angle theta with the x-axis at time t, and particle will be at point Q at t plus delta t time, and it is making an angle theta prime. So that means in delta t time it moves from this to this, so that means there is an angular displacement and linear displacement. There are two types of displacements of these particles. One is the angular displacement, and another displacement is known as simple displacement, or I can call it as linear displacement. Say if at point P it is making an angle, it's making an its position vector is r, and the position vector of this Q will be r prime, then the displacement vector is P to Q. It is nothing but it is r prime minus r vector, and let me call it as delta r. So it is the linear displacement of the particle. But on the other hand, there is a change. This angle is d theta. So this is known as angular displacement, and we call this as d theta vector, and it's also vector quantity. It's acting like this, right? And this d theta is nothing but theta prime minus theta angle, right? So that's what we can talk about it. So that means we talked about angular displacement and linear displacement. Now that means angle is changing with time. So when something is changing with time, what does that mean? That means there is a velocity. So if angle is changing, that means we have to talk about the angular velocity. So how do we define? That means that this is the change in angular displacement with time. This is known as omega, and omega is known as angular velocity. But if delta t approaches to 0, so that means we can talk about instantaneous angular velocity. In that case, it is defined as the limit delta t approaches to 0, delta theta over delta t, and we call it as d theta over dt, right? So here the unit of it is theta is taken in radian and time is second, so it is radian per second is the unit of angular velocity, and here theta is in radian. So now let us try to find out the relationship between linear and the angular velocity. So to find out now the relationship between angular displacement and angular velocity, and we have to find out this in the vector form. So now I will talk about angular displacement and angular velocity. And angular velocity in vector form. So let us draw another diagram. So it is r vector and it is point P, and after some time it will be at this Q point, and let us call it as r prime, and this is the displacement vector dr vector, right? So as we had talked about this in the previous slide, so now this r is representing P point and r prime is representing Q point, and this r prime vector can be written as r plus dr vector, and say it's making an angle theta as we are moving from r to r prime vector. It's making an angle d theta angle, right? Now d theta is the angle between r and r prime. So to incorporate d theta, what do? We will take the cross product. So if I take a cross product, I can write down r prime cross r, and it is simply mod of r vector, mod of r prime vector, and sine of d theta, and say n cap is the unit vector. N cap is the unit vector, right? But this d theta is a very small quantity. So that means sine d theta is nearly equal to written as d theta. So I can write down r, and this can be written as r, sorry, not r prime, but let me do little correction here. Yeah, it should be r and r prime, and this is r vector cross r plus dr. I just substituted its value from here, and it is mod of r and r plus dr mod d theta n cap. D theta is n cap. Now if I open this, then this can be written as r cross r and r cross dr with plus sign is equal to this one. So I can write down it as r plus dr, it's mod, and d theta vector. Now what do? Again, make this term 0 because r cross r, so it is r into r sine 0, because the angle between r and r will be same, so this will become 0. So that means I can write down it as r cross dr is equal to r plus dr mod d theta vector. So from here I can write down expression for d theta. So d theta is what? D theta comes out to be that d theta vector is equal to this r cross dr vector divided by r plus dr. So since dr is a very small quantity, so in the denominator this can be ignored. So we can simply write down it nearly equal to r cross dr r cross dr divided by mod of r square, right? So this is the expression for d theta. So this d theta, it can be written as r cross dr over mod of r square. This is expression for angular displacement in the vector form, or sometimes we can write down it simply r cross dr over r square. Now we have to find out the angular velocity. So to find out, let us proceed as follows. So for that we have to take the cross product. So to calculate angular velocity, let us proceed as follows. So let us take the cross product of d theta with respect to r. So it is r cross dr cross r vector divided by r square. So it can be written as, it is here I will use the cross product a cross b cross c. It can be written as b a c minus a b c, right? So if I use this formula here, then I can write down it as, it is dr r minus r dr whole divided by r square. So it can be written as simply r square dr minus, it is r and dr. If I try to look at the diagram, so it is, if it is, sorry, uh, yeah. So this is r vector and dr is along this direction. So both are perpendicular. So this makes this quantity 0, because r dr cos theta means cos 90 is 0. So this makes this quantity 0. So it is r square dr. It is r square dr over r square, right? And this will cancel out with it. So that means I can write down d theta cross r vector is equal to dr, and now I can rewrite this like this, d theta cross r, and dividing both sides by dt, so it is dr by dt is equal to d theta by dt cross r vector. So this is the linear velocity is equal to, and this is angular velocity, so omega cross r. So this is the relationship between linear and angular velocity. Right, so that's all. So this is the angular velocity and this is the linear velocity, and this is the relationship between them. Now let me define another very important quantity, that is angular acceleration. Now I will talk about the angular acceleration. So if there is a change in angular velocity with time, then we can define a new term as we have defined in case of linear motion acceleration. So in the similar fashion, we will define we can define a new term, and we call that as angular acceleration. And mathematically, alpha vector, it's angular acceleration, it is limit delta t approaches to 0, delta omega y, delta t, or d omega over dt. This is known as angular acceleration. Also, we know that this omega is d theta by dt. So it is d square theta by dt square. So, right. So this is another way to look at the angular acceleration. Now, till now I have defined few terms. I talk about angular displacement, I talk about angular velocity, and I try to find out the relationship between linear and the angular velocity, and I also defined the angular acceleration, right? So that's all for this lecture. This is a very basic idea of few things which you have learned in your +2 level. Now, in the next lecture, I will talk about some more important terms which are useful in the rotational motion, like inertia, torque, and moment of inertia, linear and angular momentum. So that's all for this lecture, right?